Today is February the 20th, and it's week 7. We have chapter 8 that we're talking about this week, and this has to do with the sampling distribution for the mean and confidence intervals, and those build directly on the chapter 7 stuff that I guess the homework 5 is due for this week, and quiz 5 is this week on chapter 7. So I will entertain questions on that a little bit later in class. I will also say that I've got, for those of you who took the exam in this room, I've got those exams up here during the break. You're welcome to come and collect those. The extra credit version of the midterm exam is due, I think it's due to, is it today? Thursday. Okay, Thursday midnight. So make sure you do that if you want to get any extra credit for the questions that you missed. Yeah, so I have a question that I want to ask you guys to start off. And that's not it. Okay, so I'm going to give you 5 minutes to work on this, and it has to do with the chapter 7 material, so just like what's due on Thursday night at midnight. But this is really important. We're going to talk about the normal distribution more today, but I just want to see how many of you are up to speed on this already. If in doubt, you should actually, even if you're not in doubt, you should draw the picture. So what does the picture look like for this one? We have a mean of 100, standard deviation is 16, and there's some point up here, 125, and we want the area under the curve to the right of that. So how do we do that? We can stay in the x world, actually, or we can move to the z world. If we stay in the x world, then we have just what we have written down here. We could go to Excel, and I'll show you how to do that, and calculate this directly without going to the z world. Although, let's do this by going to the z world. So 100 gets transformed to 0. 125 goes to 125 minus 100 divided by 16, which is 25 over 16, which is 1.5625. So we want to know the probability that z is greater than 1.5625. And we have a couple options for that. Let's see. In the back of the textbook, Appendix C, you can look up the value 1.56. So here's the row for 1.5, and then 0.06 is right here. So we get this 0.9406. But that's the probability. You can see from the picture, that's the probability of being to the left of that z value. And we want the probability of being to the right of that, so we're going to take 1 minus 0.9406. And that gives us the correct answer. If I wanted to use Excel for this, I could come up here and say this is equal to what do we have? So mu, sigma, and like that. So mu is 100, sigma is 16, x is 125. So probability of being greater than x, probability of being less than x, let's find that first, and then we'll find the probability of being greater than x. So probability of being less, we have norm dot dist. The x value is the first thing we put in, comma the mean, comma sigma, comma the indicator that we want a cumulative distribution or cumulative value. Whenever we're dealing with continuous random variables, almost always, at least in this class, we're always going to use a 1 here instead of a 0. That's not true for discrete. But there we go. There's the 0.940915. That's more accurate than what the chart has. And to get the probability of being bigger than that, we just take 1 minus that, 0.05901.085. So this is one way to do it. The other way to do it would be to introduce the z. So what's our z value? Our z value is going to be equal to x, so 125 minus mu divided by sigma, and there's the 1.56225, and now we want probability that z is less than z, and that's going to be equal to norm dot s dot dist and the z value, comma 1, and there we get the same 0.940915. So take 1 minus that and you get what it is we're looking for. So two different ways to do that. You can use the chart in the book. You can use Excel if you have a TI calculator. And you want to know how to do that with your with your TI-84 or whatever, come up and see me after class or during the break, and I'll show you how to do that. All those functions are built in. For the final exam, it has been scheduled, and it will be on the Tuesday of finals week, I believe. I'm not sure the exact time, but I am sure that there will be computer labs for everybody. So you will be able to use Excel in the same fashion that we did for the midterm. Those of you that had to take it on paper, you won't have to do that this time. So questions on the IQ question? Everybody's feeling comfortable? Well, probably you're not. That's okay. We'll look at some of the other homework questions. But you need to feel comfortable with this stuff, because the normal distribution and being able to do what we just did in this question with the normal distribution is foundational. Everything else you do in this class, when you get into other classes that use statistics, it's all based on this normal distribution. And part of that, or I guess the main reason for that, can be explained by this next question that I want to ask you. So let me ask you one more question. This one is multiple choice. So there are a lot of theorems out there in math and other places, but which one of those is the most useful theorem known to man? And I realize I'm only giving you 4 to choose from, so you might not agree with this list, but okay, let's see how many. 17 responses. More than half of you think it's the fundamental theorem of calculus. That's a good one, and it is very useful. But I think that the central limit theorem is actually the most useful one. And what is the central limit theorem? Why is it so useful? And I don't know, useful. How do you define that even? you could make an argument, of course, that it's not the most useful, but it's probably the most used of all theorems, especially today, because what the central limit theorem says is that if you have if you take samples, if x is a sample from any distribution or population, and the mean of x is equal to mu, and the standard deviation of x is equal to sigma, then if you have a big enough sample size, excuse me, and by big enough we mean n is greater than or equal to 30, then x bar is approximately a normal random variable with mean mu and standard deviation sigma over the squared of n. Okay, so that is actually nothing short of miraculous. I mean, this is like magic, how this works. So what this is saying is, if I'm going to take a sample from a population, if I have a big enough sample, it doesn't matter what the population looks like, what the distribution of the population looks like. If I take a big enough sample, x bar is going to be normally distributed. And that's why the normal distribution is so important. Okay, so what does that mean? If you come over here to, let's see where we want to go. If you come here to the week 7 folder, you will see the central limit theorem applet. And this describes or helps you understand what's going on with the central limit theorem. So if I have a population that looks like this, so this top distribution you see here is the population. This is a normal distribution, right? It's symmetric, it's bell-shaped, it's got all the features that we know about the normal distribution. If I want to take a sample of, say, size 25 from this distribution, I'm going to just click animated, and I can watch as those 25 observations come from this normal distribution. So they're randomly selected, and once those are all collected, the mean is calculated. And so then we have, in essence, a sample from the sampling distribution of the mean. Okay, so we want to know what that looks like. So we could do this again. I'm not going to watch it rain all day, but I'm going to take 5 of those things. So every time I click 5, it's taking 25 samples from here, calculating the mean, and then plotting that down here. Okay, so what happens is I do this a bunch of times. Just kind of click this. It's kind of like playing a video game. Try it. Let's do it 10,000 times really quickly. So if I have samples from this distribution and calculate the mean, then I can click on this fit the normal, and there's a little curve there now, and that sure enough looks like a normal distribution. Okay, so what's the mean of the population? You can see it up here. I don't know if you can see it, but when you try this on your own, you can see it is 16. What's the mean of the sample? Or the mean of all of these sample means is also 16. Okay, what about the standard deviation? Standard deviation, so let's come back over here. So the expected value of x bar is equal to the expected value of x is equal to mu. And in this case, we have 16 for both of those. The standard deviation of x is equal to, you can see it here, it's equal to 5. So this is sigma, this is 5. So the standard deviation of x bar should be sigma over the square root of n. In this case, it should be 5 over the square root of 25, which is 1. And if we come over here and look at our sample standard deviation, we have 1.02, which is pretty close to 1. The more samples I take, the closer that's going to become 1. Okay, so 1.02 is what we have right now. Now, with the underlying population being normal, you might not think that's such a big deal. And so let's see what happens if we change to a uniform distribution. Now, this applet, for some reason, doesn't let you take more than 25 samples. So we haven't actually had the central limit theorem kick in yet, because it says you got to be bigger than 30 or more, in order for it generally to be accepted. But you can see what's going on even with just 25 samples, that we're getting a normal distribution. Okay, so again, animated, here's what they look like. These are coming from everywhere and should be uniformly distributed across all the values from 0 to 32. Again, note the mean is 16 up here. Standard deviation is 9.52. And if we do this again and again and again and again, look what we're getting. We're getting what appears to be samples from normal distribution. And maybe we have to take a whole bunch in order to really show it. Okay, so this is coming from a uniform distribution. X bar is normal, even with a sample size 25. Turns out there's some very sophisticated math that shows that this is really true. If you take x bar, you can write down the probability density function, and then turns out as n gets large, it turns into a normal distribution function, which is kind of crazy. Okay, what about a discrete random variable? So if I come over here to custom, I can put in okay, we'll just go with this. Okay, so if I'm going to sample from this thing, I'm getting a bunch more over here than I get down here, but I don't get anything in the middle, right? What's the mean going to be? The mean's going to be 21.32 right here. So if I do this over and over and over again, the sample means are represented by this distribution here, which now n is 25. That's not quite big enough, but you can see what's happening. If they would let me increase this to n is 30 or 35 or something else like that, it would look more and more like the normal distribution. Although you can see that it's filling in kind of nicely. Okay, so central limit theorem is extremely useful because, or rather I say it's the most used, probably the most used theorem known to man, because every time people are collecting data, they're saying what's the mean of the distribution? What is mu? We want to know about mu, and in order to know about mu, it doesn't matter what the underlying distribution type is. We can get an estimate in fact, we say a point estimate for mu. What is that? That's just a single value that we say is our estimate. So mu is what? What's the best point estimator, do you think? It's out there? X bar. That's the sample mean. Okay? So if we said that X bar is normal, with mean mu and standard deviation sigma over the square root of n, what's the probability that X bar is equal to mu? So we've got this point estimator. We're saying it's the best point estimator. There's some fancy properties that X bar actually has that makes this one the best estimator, at least for some criteria. But what's the probability X bar is actually equal to mu? That probability is 0. Exactly right. Why is it 0? Because X bar is a continuous random variable. So probability it's equal to anything is 0. In fact, if we're talking about continuous random variables, when we talk about probabilities, we're really talking about the area under the curve in a certain region. So if we have a single point under the curve, here's mu, and we say, what's the probability that x is equal to mu, or x bar is equal to mu? That's just the width of that line times the height, and the width is 0 because it's a single point. Okay, so this is always going to be 0, not just for mu. Okay, so that doesn't mean that x bar is useless. It's wrong. It's always wrong, but that doesn't mean it's not useful. If I take x bar and I add and subtract a little bit, then I have what's called an interval estimate. And in this case, we'll say we have a confidence interval for mu. And this confidence interval very much is based on the assumption that we either have a big sample size and the central limit theorem kicks in, or the population we're sampling from is normal, because that's x bar is still going to be normal if x is normal. Okay, so what is this? What is this? This is the first introduction you're having to statistical inference. If I want to make inference about the population parameter mu, this is the first tool we have for doing that. In other words, we're making a clear demarcation today from probability and everything we learned in the first part of class and statistical inference. Okay, so you're going to see the same story over and over and over again. When you guys were little and your parents wanted you to go to bed and it was late and they were tired and you wanted to stay up and they said, okay, no, it's time for bed, what'd you say? This was back before iPads put kids to bed. He said, tell me a story. If you tell me a story, I'll be able to go to bed. And they're like, okay, I've told you a story every night for the last 5 years. What can I do tonight to make the story any different than last night? And it turns out there's nothing they can do to make the story different except change the details. Instead of a black horse, the hero is riding a white horse. Instead of a mountain they have to climb, it's a beanstalk or the top of a castle or whatever it is. It's really the same story. Well, the story is important and the details are going to change, but that's exactly what's going on here in this class. We've got a confidence interval for mu. That means, all it means is we're trying to estimate mu, estimate a parameter. Well, what if we wanted to know about a confidence interval for pi, population proportion? What do you think we're going to do there? Well, our point estimator is going to be p. Remember, p is equal to the number of successes divided by the number of trials. And it turns out, if the sample size is large enough, and the criteria is a little bit different than with the mean, but if the criteria is met, and what is the criteria? The criteria is n times pi and n times 1 minus pi are both greater than or equal to, I don't know if it's 5 or 10 for this textbook, but some textbooks say 5, some say 10. You can use either if you like. But it turns out this is also going to be normal. So the mean is pi, and the standard deviation is pi times 1 minus pi over n, square root of that. Okay, so if we know what the distribution of x bar is, we can use that to make statements about how big the interval should be. Well, we can do the same thing with p. we have p plus or minus z, and z comes from the normal distribution times the square root of p times 1 minus p over n. Why are we using p here in the standard deviation instead of pi? Well, because we don't know what pi is. So we're estimating that even in this confidence interval. Okay, so we have confidence interval for pi. And you can kind of see a general form here. What if I had two populations I was interested in? Men and women, let's say. And I want to know what the average starting salary is for men and for women. And I don't really care about them separately, but what I really want to know is one higher than the other. So I could say, what's a confidence interval for mu1 minus mu2? Well, the first question I should ask myself is, what's the point estimator for mu1 minus mu2? And what do you think that's going to be? It's going to be x1 bar minus x2 bar. And then point estimators are always wrong, so I need some measure of variability, z, or maybe some other random variable, we'll stick with z for now, times sigma sub x1 bar minus x2 bar. So I'm not going to get into the details here because this is something beyond the scope of this course. When you take stat202, you will get into this particular example. But what I'm trying to get you to understand is it's exactly the same story, just the details are a little bit different. Right? If I have a parameter mu1 minus mu2, if my confidence interval contains 0, then that says that mu1 should be considered to be equal to mu2 at that level of confidence. So what do I mean by level of confidence? Alpha is the confidence, actually 1 minus alpha is the confidence level. So if I'm 95% confident about something, that means alpha is 5%. Okay, and we'll talk more next week when we talk about hypothesis testing about alpha. But if I wanted a 95% confidence interval for mu, that's going to be x bar plus or minus z sub 0.025 times sigma over the square root of n. So what do I mean by 0.025? I want the z value that has 2.5% the area to the right of it. Why do I want 2.5% for a 95% interval? Because I want 95% in the middle. So I've got another value which you could write as z sub 0.975, but that's just negative z sub 0.025. Okay, so we've got some symmetry going on here with the normal distribution. You can see, again, the normal distribution is very important, and it's very important that you understand how to use the normal distribution and look at it and say, oh, okay, these are the regions that I'm interested in, and I want the probability associated with some value and so forth. Okay, so confidence intervals, what do they really mean? So I calculate this interval, it's two numbers, x bar, that comes from the sample, z, that comes from the normal table or from Excel, multiply it by sigma over the square root of n. It's assuming that I know what sigma is. If I don't know what sigma is, guess what? It's the same story, just the details are a little different, right? So what is this saying? It says take a sample, create x bar, and then add and subtract a little bit to that. A margin of error is one way they describe this. There are other names for this part, but in this class we'll say margin of error. if we do this, we get what we call a 1 minus alpha times 100% confidence interval, which means that we can have a certain level of confidence that the interval contains a true value. So what does that mean? That means if I repeat the experiment and I take X bar from lots of different samples of the same sample size from the same population, but they're different samples, I'm going to get different values of X bar. And it turns out that if I do this over and over and over and over again, then there's a certain portion, in fact it's 1 minus alpha, is the proportion of the total confidence intervals produced that contain the true value. Does that make sense? So it's kind of like shooting free throws. If you get Steph Curry shoots, what does he shoot? 93%? We'll just call it 95%. Shoots 95% free throws, and if there's a technical foul, he's the one that you want to go and shoot because he makes 95% of the free throws. Does that mean he's going to make, I mean, what does it mean then when he goes to shoot the free throw? Would you say there's a 95% probability he's going to make the free throw? Well, it turns out that that's not the correct way to think about probability. You can be 95% certain that he's going to make the free throw, but once he goes through his little routine and the ball's in the air, then it's deterministic at that point. You still don't know the outcome, but it's either going to go in or it's not going to go in, and it doesn't really make sense to talk about probability in that sense, or in that case. Instead, you talk about confidence. Okay, but in the long run, you'd say the proportion or the probability, the proportion that are successful is going to be 95%. So this is kind of like a binomial distribution. If you go over here to the week 7 folder, there's another applet called the confidence interval applet. And if you click on proportion or click on method and select means and just leave everything else the same and click on sample, you'll see a confidence interval that's produced. So the average value is this little black dot, and then you're adding and subtracting, and the true value of mu is 0.5, and that's in the interval. Okay, so that's like Steph Curry went and shot a free throw and he made the free throw. And if he makes 95% of his free throws, or we're 95% confident, then he takes another shot and he makes that one, and so on and so forth. Eventually he's going to miss some. You saw one that he just missed and another one that he missed. But in the long run, he's going to make 95% of these things. So in other words, if you were to repeat the experiment 100 times, 95% of the intervals would contain the true value. And you can do that all at once by just changing the number of intervals and then clicking sample. And you can see there are 1, 2, 3, 4, 5, 6, 7 of the intervals that don't contain the true value. Now that's kind of like what? Like the, there you go. That's kind of like the binomial random variable, isn't it? If somebody shoots 95% free throw rate and they shoot 100 free throws, are they going to hit exactly 95? Probably not. 97, 94, 93, they might get 95. So if we keep sampling, you can see in the long run, in fact, if you want to take more samples, you can put 10,000 in here all at once. And I don't know if it's listing all 10,000 of those. Probably not. But you can see that of the 12,322 intervals that were created, 11,657 or 94.6% contain the true value. So that's what's going on with confidence intervals. But when we do confidence intervals, we're just looking at a single interval. So we're just doing it one time. Okay, so you should go and play with this. It's kind of fun. You can change the confidence level if you want. So if I put in 99% and say recalculate, it goes back for, I guess it only does 10,000 here. Oh, it redoes the sample, so it's not the same. It's not looking in the past, but you can see that of the 10,000, 9,892 have the true value in it. If I take another sample, another one, and another one, in the long run, this is going to converge to 99%. That's what we mean by a 99% confidence interval. Okay, it's a statistics faux pas to say that there's a 99% probability that mu is in the interval, though. You don't. That's the wrong use of the term probability, and if you do it, someone will call you on it and say, "Hey, you didn't pay attention in your stat201 class." So don't do that. Okay, so questions about the central limit theorem or confidence intervals? No? All right. So I am going to ask you guys if you have questions about homework number 5. So why don't we establish if there are any of those, and then we'll take just a short break. I'll hand out exams, and then we'll jump into the homework and see how far that takes us. So any questions from homework 5? Okay, 7, 2, 4. All right, I'll throw 9 in too, because I think people will have trouble with that one. Okay, so let's take just a short break. We won't take I'll pass out the exams, and then then we'll start back up. All right, the standard normal area for each of the following, or find the standard normal area for each of the following. The first one says probability that z is between 1.24 and 2.14. So this is number 2. A says, what's the probability that z is between 1.24 and 2.14? Did I write that down right? Yeah. Okay. So what's the first thing I should do? Draw a picture. If I draw the picture right, probably I'll get the question right. So standard normal, that's z. So here's 0, here's 1.24, and here's 2.14. Right, so how am I going to find this area? If I were to look up 2.14 in the table in the book, which I certainly can do, I see here's 2.14, so here's 2.1, and then I come over here to 4, and I get 0.9838. The right value. So the probability of being less than 2.14 is 0.9838, and that's the area from here all the way down to here. All right, but I don't want all of that. I just want part of it. In fact, the part I don't want is everything to the left of 1.24. So what's the probability that z is less than 1.24? So I need to look up 1.24 in the text. On the chart, here's 1.2, and the 4 column is right here, so 0.8925. Okay, so I take the difference between those things and I get the right answer. If I want to use Excel to do this, homework 5.2, I would say here's A, here's B, and now what's the probability that A is less than Z, less than B? So I have A is 1.24, B is 2.14, and to get the probability of being less than or in that range, I'm going to take norm.s.dist, and I'm going to put B in first, comma 1. When I'm using, again, when I'm using continuous random variables in this course, I'm always going to put it on 1 right here, because that says cumulative probability, so it says area under the curve, and that's what I want here. So minus norm.s dist and norm.s.dist A comma 1, and I get that value there. So I'll come back over here, plug it in, and do the same sort of thing for the rest of these. The only one that's any different is the last one that says what's the probability that Z is greater than 0.53. And you say I got that right. So the probability of being greater than 0.53, so again I'm going to draw the picture. It's part D. Here's 0.53. So the probability that Z is greater than 0.53 is 1 minus probability that Z is less than 0.53. So I can either look up 0.53 in the text, or I can say what's the probability, so norm.s.dist 0.53 comma 1, that's going to be the probability of being to the left, and so I actually want 1 minus that, probability of being to the right. So again, if I wanted to use the table in the back of the book, I could do that by saying, where's 0.53? Here's 0.53 is 0.7019, and I want, again, the table is telling me the left tail probability, so I want the right tail probability, so I have to subtract that from 1. So 0.29856. Let's try that again. I put an extra. Now this should get it. There we go. Okay, so that's number 2. So questions on that? Are we good on that? Number 4. Credit scores of 35-year-olds applying for a mortgage are normally distributed with a mean of 600 and standard deviation of 65. Find the credit score that defines the upper 20%. So if we define the upper 20%, what does that mean? Draw the picture. 20% is up here, 80% is down here. We want to know what's the X value that has 20% of the area to the right of it. And we know that the mean is 600 and the standard deviation is 65. So this is going to be 600 plus the Z value that has 20% of the area to the right of it times 65. And what's the Z value that has 20% of the area to the right of it? So this is the X world. Here's the Z world, and in the X world 600, and the Z world is 0, and this is just Z sub 0.2. What's by the way, what's another name for this X value, X sub 0.2? it's the 80th percentile, because it has 80% of the area to the left of it. So we want the value that has 20% to the right or 80% to the left. So if I come down here and look in the body of the table for 0.8, I see that happens somewhere between these two numbers, which are 0.84 and 0.85. So somewhere between there I have those numbers. So this is 0.845, let's just call it that. We'll look it up with Excel, a little more precision. But I just need to plug that in, multiply by 65, and then add 100 to it, and I get the correct value. So homework 5.4, mu sigma, I'll call it alpha. That's the value of the area to the right. So mu is 600, sigma is 65, alpha is 0.2, and so z sub alpha is going to be equal to norm dot s dot, instead of dist, now I'm going to do inverse. Norm dot s dot inverse. That says give me the probability, and I'll tell you which value of z has that much probability to the left of it. So if I say 0.2, that's going to give me the wrong value. So I actually want 1 minus alpha. So 1 minus 0.2. And here it is, 0.841621. So x of alpha is going to be equal to mu plus z times sigma. So 654.7. Let's come back over here. $654.7. Part B says 85% of the customers have a credit score higher than what value? So again, draw the picture. Even if you're not in doubt, draw the picture. So this is saying 85% is bigger than what value? So we have x sub 0.8 sub 0.85. We have 0.85 here. 85% or bigger than that x, and so this x is going to be equal to, same thing, 600 plus z sub 0.85 times 65. Okay, so what's different here? Does that formula that I wrote down look right? I'm saying 600 plus some number, but I drew the picture so that the number is to the left of 600. Is that okay? Yeah, that's okay. Why? Because the z value is actually going to be negative. It's going to be negative, I don't know what, we'll figure it out. If there's 85% to the right, that means there's 15% to the left. If I want to use the table, I'm going to come in here and look for 0.15. And I'm going to see, where's 0.15? It's right here. Look at that. So negative, sorry, I want 0.15, not 0.05. Not 0.015, I want 0.15. So that's the wrong value. I'm looking for something between these values. So that's negative 1.03 or 1.04. Negative 1.035, let's say. And if we use Excel, all we have to do is change our alpha level. instead of having 20% to the right, we have 85% to the right, so I'm going to change that to 0.85. There's my z value, negative 1.36, and my alpha is 532. Come back over here, paste it in. And then finally, part C says, within what range would the middle 90% of the credit scores lie? We've got 90% in the middle. Again, draw the picture. If I have 90% in the middle, how much do I have in each tail? I've got 5% in each tail. So this is going to be 600 plus z sub 0.05 times 65. This is going to be 600 plus z sub 0.95 times 65. So z sub 0.95 and z sub 0.05 are the same number in absolute value, but one's negative and one's positive. So that actually makes this not too difficult. I could come over here and look it up, 0.95. You see this is not as easy or fun, but here it is, 0.94 and 0.95. Right there, 1.645. That's a value that you probably will see a lot. So 1.645, negative 1.645. If I wanted to use this, I can just copy and paste, change my alpha level to 0.05. That's going to give me the right end, so 706. That's the top end. And if I want the bottom end, I'm going to change alpha to 0.95. See what it does to the z value. Changes it to negative. So I get 493. And let's check our work. That looks good. So questions on that? Everybody see what's going on with the Excel and with the chart? Your TI 84, 83, 85 calculator can also do this. If you don't know how to make it do it, come talk to me and we'll figure it out. So that's number 4. So let's look at number 7. .7. Alright, between 11 p.m. and midnight on Thursday night, Mystery Pizza gets an average of 4.6 telephone orders per hour. Part A says, find the probability that at least 29 minutes will elapse before the next phone order. Part B says the probability that less than 24 minutes will elapse. And part C, find the probability that between 24 and 29 minutes will elapse. So part A and B are kind of setting us up for part C, maybe. What's going on here? We've got what kind of random variable are we using? So if you think about arrivals, the number of arrivals per hour of calls at a pizza place, that's kind of similar to the number of hits you get on a web page, the number of subscribers on your YouTube channel, the number of potholes on Market Street as you're driving, the number of neutrinos that show up in a physics experiment, the number of defects in a manufacturing process per unit produced. So that's a Poisson random variable. And closely related to the Poisson is the exponential random variable, which says instead of counting the number of occurrences, it says how long does it take until the next occurrence. So if the Poisson random variable has a mean lambda, which is the number of occurrences per unit time space or whatever. Then the exponential also has that parameter lambda, but the expected value, so if x is exponential, then the expected value of x, I mean, this is a waiting time. So if you get, on average, 10 phone calls per hour, how long do you wait between phone calls on average? Well, it's every 6 minutes on average. Let's figure to average that out, right? So the expected value of the exponential random variable is 1 divided by lambda. And that puts you in the right units. It's minutes per occurrence, right? Okay, so in this question, they're talking about the time elapsing before the next phone call. So they get 4.6 phone calls per order. So lambda is 4.6 calls per, not per order, but per hour. So the expected value is 1 divided by 4.6 hours per call. All right, so whatever that turns out to be. You can convert it to minutes if you want. You can leave it in hours. Here we're dealing with hours, so well, the first part of the question gives us lambda in hours, but the next part here says in minutes. So what's the probability that at least 29 minutes elapse before? So part A says, what's the probability that x is greater than 29 minutes? And an exponential distribution looks like this. So we're going to say here's 29 minutes. What's the probability of being bigger than 29? Okay. So properties of the exponential distribution, and I wrote this down wrong in my last class and ran into trouble, so make sure you get this written down right. The probability density function is lambda times e to the minus lambda x. And I wrote it down as 1 over lambda times e to the minus 1 over lambda times x, which is actually a valid probability distribution, but it's parameterized different. So this is what we want to use, and it turns out that the probability that x is less than or equal to x, or this cumulative distribution function, can be written down as 1 minus e to the minus lambda x. So that's the probability to the left of x, and so the probability to the right of x is just going to be 1 minus that, or e to the minus lambda x. So as long as lambda and x are in the same units, I can just multiply these things together. So if I have 29 minutes, how many hours is that? In other words, if I want to know the probability that x is greater than 29 minutes, that's e to the minus lambda. Well, lambda is in hours, so 4.6 times 29, but 29 is in minutes, so 29 over what? Over 60. That will put everything on the same scale. So I can plug that into my calculator, or I can say so this is homework 5.7, part A. So A is going to be 29, so probability of lambda. Lambda is 4.6. So probability that x is greater than A is going to be equal to exp negative lambda times x divided by 60. So it should be about a 10% probability, almost 11%. Okay, so let's plug this in. Let's check our work just to make sure we're heading on the right track. We are. All right, part B says find the probability that less than 24 minutes will elapse. So what does that mean? Less than 24 minutes. Probability x is less than 24. So again, I'm going to draw the picture. Here's 24. I want that. And this is going to be 1 minus e to the minus lambda x. So in this case, 1 minus e to the minus lambda, which is 4.6, times 24 over 60. Again, it's very important that I get those in the right scale. So here I've got 24, 4.6. I'm going to copy that and paste it, but I actually don't want that. I want the probability. I want 1 minus that. So I want p of x, x being less than a, and that's just going to be equal to 1 minus that thing. So 84.1183%. And this is taking a while, so we'll come back to that. So part C says, what's the probability of being between 24 and 29? So again, draw the picture. Here's 29, here's 24. So this is going to be the probability that x is less than 29 minus the probability that x is less than 24. Now with the other distributions, we use functions like norm.dist and binom.dist and so forth. There is a function built into Excel called exponential.dist, so you can use that one as well if you like. So let's see if we can match this up. So we have probability that x is less than 29. That's this number here, 0.891752, and we want to subtract from that. So here we want probability that a is less than x, less than b, where b is 29 and whatever a is 24. So this is going to be equal to this first one minus the second one, so 0.05. Let's copy that, paste that in, and then check the work. We got it right. We're good. But let me just show you real quickly the exponential distribution function. So we should be able to get these same exact values by taking expon.dist. X is the that value, lambda is that value, and I want cumulative. And when I push enter, am I going to get the right answer? No, I'm not. Why? Because I didn't divide by 60 right here. So I'm going to divide that by 60, and I should get the right answer. So I get the same answer if I do that one. Okay, so questions on that one? Other questions? We good on that one? All right, let's look at a number 11. Well, let's see. What's number 11 about? Let's do number 11, and then we'll go back to number 9. And if there are no other questions, then we'll be done at that point. Okay, so we have three functions. F of x is 0.6, between 0 and 4. f of x is 4 minus 1 times x for x between 0 and 4. And the last one is f of x is equal to 0.025 times x for x between 0 and 4. So all of these functions are defined between 0 and 4. All right, so here's 0, here's 4. The first one says the height is 0.6, like that. The second one says 4 minus x. So if x is 0, what do we get? We get 4. This is going to be way up here. 4, and then it's a straight line. And I'm going to put number 4 right here. Okay, so we have that function, and then the last one says 0.0125 times x. So it starts here at 0, and 0.125, that's an eighth, isn't it? So an eighth of 4 should be 2, so it comes up to about right here, like this. All right, so those are our 3 functions. The question is, which of those could be probability density functions for a continuous random variable? So what do we need for a probability density function? They all have to be positive, so they all have that, or at least non-negative. The area under the curve has to be equal to 1. That's what you want to check here. So the first one has a height of 0.6 and a length of 4. So what's 4 times 0.6? In other words, the area under the curve here, is it 1? No, it's 2.4, isn't it? Yeah, so that one's out. So part A, that one's out. B says, it's the second one here, the area under the curve from, so we go from 4 down to 0, from 4 to 0. So what's the area under the curve? We just have to know what's the area of a triangle. 1/2 the base times the height. So what's the height? The height is 4. The base is 4. So the area is 8. So that can't be a probability distribution, can it? All right, so it's 2, yeah. So B is out. And finally, if the other 2 are out, that means C has to be our value, or it has to be the right answer. But what's the area under the curve? Well, the height here is 2. So 1/2 the base. Sorry, the height's not 2, is it? I got that wrong. The height is 1/2. So I drew that picture wrong. So let me get rid of this other part. There's 0.6. Here's 0.5. Is that right? If it's, yeah, 4 times an eighth is 1/2, not 2. So my bad. So we have height of 0.5. So 1/2 the base, which is 4. So 1/2 of 4 is 2. Times 0.5 is going to be 1. And that's going to be the right answer. So let's C should be the right answer. We got it right. All right, so let's look at number 9 then. And unless there are other questions, this will be the last thing we look at today. So if you have other questions, don't hesitate to ask. This says the mean life of a certain computer hard disk in continual use is 7 years. So this is going to be an exponential distribution again. So the expected value of x is 7 years per disk. Did I spell that right? Disk has a K or a C. Disk. All right, so what does that mean our lambda is? So x is going to be exponential lambda. So what is lambda? Lambda should be 1/7 disks per year. All right, that's the number of disks that fail per year. So 1/7 per year fail. Does that make sense? So think of the Poisson random variable that's saying how many occurrences do I have per year? Well, it's 1/7. That means it takes 7 years on average for each to fail. That's good. It's just like you get 10 phone calls per hour. It's 6 minutes between phone calls on average. Same thing here. So part A says how long a warranty should be offered. I think they meant to say how long of a warranty should be offered if the vendor wants to ensure that not more than 27% of the hard disks will fail within the warranty period. So this is a little bit confusing, the wording here, but we've got an exponential distribution. It goes down like this. And they want to find out what this x value is such that 27% is to the left of that. All right. They don't want more than 27% of the hard drives failing before the warranty period is up. Right? Because if they have more than 27% fail before the warranty, that means that they're, I don't know how they came up with 27, but that means they're going to be refunding or refurbishing too many units. Because they think 27% is okay. If the warranty period's long enough, then by that point people will just say they're obsolete anyway and go buy new ones. So 27%, we want that to be the probability below x. And so the question is, what is x? So I will write this as x sub 0.73. So we have 73% to the right of it. And we know that the probability that x is bigger than x sub 0.73 is equal to e to the minus lambda x. Right? So I can, and this is the x that I'm interested in right there. So I can write this as 0.73 is equal to e to the minus lambda x, and now I just need to solve that for x. So if I take the log of both sides, I get the natural log of 0.73 is equal to minus lambda x, and so x is equal to negative 1 over lambda natural log of 0.73. And 1 over lambda is 7, just 7. So if I plug these numbers in, I get negative 7 natural log of 0.73. So let's come over here to Excel to do this. Let's see, let's put in alpha. Alpha is going to be the tell probability on the right, so I'm going to put 7.73. And actually, let's cut that and paste it. Let's say this is warranty percentage. We'll just put that in as 0.27. And so alpha is going to be 1 minus that. And we want x is going to be equal to, we've got to have a lambda. Lambda is 7. Sorry, lambda is 1 over 7. January 1st, let's make that a number. And so x is going to be equal to negative 1 over lambda times the natural log of alpha. So 2.2 years is what they should offer the warranty for. And then part B says, how long should the warranty be offered if we want to ensure that not more than 47% of the hard drives fail? So, same thing. Copy, paste. Instead of 0.27, we're going to put 0.47, and we get 4.4 years. Does that make sense? If I come back and look at the picture, here's 27%. If I put in x of 0.47, that's x of 0.53. So that means I've got, let me change colors. So down here I've got 0.47, which means I have 0.53 up here. Okay, so if I have 47% to the left of some number, that's going to be bigger than the number that has 27% to the left of it. So we get 2.2 or 4.44 years. Okay, so other questions about homework 5? Number 5. Oh, we didn't. You want to do number 7? Yeah. So we want to know the probability of being between 24 and 29. So we just said that's the probability of being less than 29, all the way down to here, minus the part that's less than 24. So probability of, so what we did over here was we said, here's the probability of being less than 29, here's the probability of being less than 24. Yeah, so I labeled this poorly. Let me just insert. Let's say, just insert, why can I insert? Insert, shift right. All right, so let's call this A. No, let's call that B. Call that A. And then move that to an A. Okay, so there's A, there's B. Now this is correct. All right, so we're saying what's the probability of being less than an A or B? We call that X. Yeah, so it's just like all circular. Okay, other questions? Okay, then I will stay here until the last of you leave. So if you do have other questions that you don't want to ask in front of the entire class, that's fine. Otherwise, we'll see you guys a week from today. What's that?
11.
Number 11?
Yeah.
Yeah, hang on.
What the question is?
Just a second. Let me just save this real quick.
Okay, I see the answer for the midterm.
Did you get, is that your midterm there?
Yeah.
Yeah, so you got to go into Blackboard and, not Black, yeah. And do you have your computer here?
Wrong battery.
Oh, okay. Well, let me show you how to do it.
Okay.
And then, or if you want to come to my office right now, I can just show you the answers there as well.
Okay.
But they are on Connect or Blackboard, so you can go in and see. The numbers will be different, but you just have to change the numbers around.
I can go to your office. I go to your office.
Yeah, that's fine. Let me just answer other questions here and then. Okay, so you want to look at number 11? Okay, so I probably should have drawn this in 3 different pictures instead of one on top of the other. So here's A, here's B,
okay.
and here's C.
I see.
Alright, so A says you've got 0.6. That's the height, and it goes all the way over to 4. So what's the area under the curve? So this area is 2.4. So that can't be a probability distribution. It adds up to more than 1.
Oh, so I see.
Right? So the area under the curve has to be equal to 1 because that represents the sum of all the probabilities. So you could rescale this if you wanted. If you multiplied by 1 over 2.4, 0.6 times 1 over 2.4. Sure.